So it's going to be all math today. I'm going to prove Plancherel's theorem and a little bit of math review, basically. So first, let's talk about double integrals. And how we can move variables around them. So if I have the double integral of f of x, g of y, dx, dy, it's also equivalent to write f of x integral g of y, where I need to integrate dy first, then I need to integrate the whole dx. Or I could flip them around. Fubini's theorem allows us to switch these two. Can't switch, but you gotta make sure that all the y's goes away. Like when we've done with this integral, all the y's go away, and then all the x goes away. Another example is f of x, y, g of x, dx, dy. So if you get that, this can be integrated with x and y, but this must be integrated. Must be integrated by x and y, but this need to be integrated by only x. So it can only be written in this form, however. Notice I put dy first and dx. However, if you have this, f of xy, g of xy, dx, dy, you can't really move. You only can do this. Because you need to integrate both variables. You need to gun down both variables. Basically, every time when you integrate, you gun down a variable. And for example, if you put this on the outside, you only gun down x. You only gun down the x. Like for example, if you have a situation like this, this will eliminate all the x, so there's nothing to integrate. There's nothing to integrate this portion anymore. So you can't do that, but you only can do this. You must gun down a variable. Basically, every time you integrate, you gun down a variable. So that is for double integrals. It also works for triple integrals. It's just one more extra dimension. So for a wave packet, let's talk about Fourier thing. So Fourier transform. And what it is essentially when you have, for example, we're not talking about time, psi of x equals to 1 over square root of 2 pi. From negative infinity to infinity. And you have the amplitude k, and then you got e to the I kx dk, basically a superposition of plane waves. And from Fourier transform, you can get that this thing, the amplitude, equals to 1 over square root of 2 pi integral from negative infinity to infinity psi of x e to the minus ikx dx. Notice that this is dk, this is dk. Okay. So I'm going to derive a delta function from the Fourier transform of these two equations, and I'll explain further what the delta function does. So first, let x prime be a dummy variable. And this will get us equals to 1 over square root 2 pi. Psi of x prime e to the minus I k x prime dx prime, sorry. Okay, there. And what are we going to do? We're going to substitute this in. Let's call this equation 1, and we're going to substitute it into this psi equation. Basically sub in. And what we're going to get is psi of x equals to 1 over square root 2 pi integral. That's a really bad integral. Negative infinity to infinity. Now we're going to sub in that whole part. See, we have a double integral now. Psi of x prime e to the minus I k x prime dx prime dk. Wait, sorry, that's not dk. That's e to the I kx dk. Okay, now we need to simplify this. So how are we going to simplify this? So first, the 1 over square root of 2 pi, we can just first multiply it in. Get this out of the way first. Okay. And what now? So first, let's do this. What if we do this? We manipulate this part. And we put psi of x out. But we get this part. E to the minus I k x prime times e to the I k x. And then we can put a dk right here. So we first eliminate all the k's. And then we have dx prime. So it just should be an integral right here. Okay, so what is that going to be? That's going to be equal negative infinity psi of x prime. Okay. Infinity. dk, and we need to take care of the x prime, so dx prime must be out here. And what will we have here? Well, we know that this thing equals to psi of x, and we know that a delta function has this mathematical property. X prime notice that this is our f of x prime. This is our delta. Sorry, this is prime right here. And dx. So notice how here we have x minus x prime, and over here we have x prime minus x. It's okay because one of the properties of the delta function is that, for example, delta of y equals delta of negative y, that it has symmetry. It is essentially a symmetrical function. So if we let y equals to x minus x prime, it'll be obvious that this thing will equal to this thing. So it's okay. So it's fine. That means we get psi of x prime, and we have that x dx prime, and that will equal to psi of x. This means that the entire point of this entire derivation that we have here is to prove the delta function. Not prove the delta function, but find a relationship of the delta function within. So we conclude that this psi of x minus x prime equals psi of x prime minus x equals to 1 over 2 pi integral of negative infinity to infinity e to the I k x minus x prime, or I could say, yeah, equals to that. That, or 1 over 2 pi infinity to infinity e to the I k x prime minus x, because of the symmetry. Oh, sorry, and that's going to be dk. Yeah, that's going to be a dk right there. Okay, great. So let's move on to Plancherel's theorem. And the very first thing we're going to do is something really similar to what we just did. We know that we recall that we know that psi of x equals to 1 over square root of 2 pi, the integral of from negative infinity to infinity, amplitude k, e to the I kx dk. And we know this. This is what we just got from the Fourier transform. Dx. Great. And let's consider the normalization from the definition of what wave functions do. We get this. And what it basically is that, for example, if we let that is basically this. Dx, and if we let psi of x equal to 1 over square root of 2 pi integral of k prime e to the I k prime x dk prime, and k is the dummy variable. It's a dummy variable. We get this. We're basically substituting to the complex conjugate of this as well. And what we have is, when we sub those two in, we get 1 over 2 pi, because we have 2 of these. We get a triple integral. Infinity to infinity. Star k e to the minus I kx dk, and the integral of negative infinity to infinity k prime e to the I k prime x dk prime, and that's dx. Great. Now, what we have here? We can move these two integrals. I'm going to not draw the infinity signs anymore, so that's gonna get you this. Okay. Both of them can be moved out. And if we multiply both of the e's, the exponentials together, q pi e to the I k prime minus k x dx dk d prime. So sorry, that's kind of close together. And this thing is a delta function, similar to the form that we just derived up here. This is why I derived it first, and just k prime minus k. And what we'll get is this. We can move these two back in. Okay, prime. And we get the k prime minus k dk prime times dk. And thus we get, and from the form, we get that this dk equals that. So that's Plancherel's theorem.